Morning, folks. Sorry I'm a little bit late today. Couldn't find my iPad, oddly enough. I guess my wife was watching some Netflix and just put it away. I didn't know where she found it, or left it. So around 8:58, I kind of just sat down at my desk and was like, oh, where'd my iPad go? And just had to go on a little scavenger hunt. But I found it. And we're all ready to go now, so we'll just wait for a few more people to show up. Looks like people are starting to stream in here, so that's good. Yeah. Yeah, that's what I like. Yeah, I'm not late. You guys are just early. What are you doing here already? Okay. Hello. Really good coffee this morning. My friend ordered some coffee directly from Colombia. I'm not sure why he wanted to do that, but he did, and he asked if I wanted some, so I did, and this coffee is absolutely fantastic. Okay, looks like we got about 15 people. Good morning, folks. So we'll get started. So last class we were looking at approximating square roots, and I think that a lot of us had done it already. Some of us, it was, oh yeah, you want some coffee, I know you do. Yeah, I think a lot of us had seen that sort of thing before. So what we're going to do now is we're going to sort of continue on with our exploration of square roots and things like that. But I want to show you how to write square roots in a different way, using a different type of notation. In particular, I want to show you how to write a square root using exponents. Because I think that we're all a little bit familiar with exponents, but yeah, the thing about exponents is that they're quite versatile. You can use them to describe all sorts of things. So what we'll do today, so what I'm going to talk about today is exponential notation. Exponential notation. This is our goal for today. We're going to learn about exponential notation. I'd like to show you a few exponent rules. So I think that these are rules that you have seen already. In fact, I'm like pretty much 100% sure about it. So you already know the exponent rules. I also want to show you how we can use fractional exponents and what they look like. So fractional exponents. Okay, so basically fractional exponents, what that looks like, so what this is roots or radicals. So square roots and radicals, cube roots, all of that fun stuff, they can always be expressed with an exponent. As a matter of fact, it's whenever a exponent is a fraction, that is really just code for it being a radical of some kind, and I'll show you why. So let's just do a quick review of exponents and some of the exponent rules, and then let's see if we have time for fractional exponents. Okay. So, oh, Kima just startled me. Okay, so fractional exponents. Okay, so what is an exponent? So exponent really means repeated multiplication, right? Repeated multiplication. Okay, so if I have like 2 to the power of 5, that's equal to 2 times 2 times 2 times 2 times 2, and there are 5 of these, so 5 times, right? So when people first start learning about exponents, they often confuse it with multiplication. I can't tell you how many times I've seen someone in grade 7 say that 2 to the power of 5 is equal to 10. It is not equal to 10, it's equal to 32. Okay, because 2 times 2 is 4, times 2 is 8, 16, 32, right? So don't make that mistake. But I think we're past that. I'm certain we're past that. Okay, so I want to show you a little, just a few facts. So here are some facts. Okay, so the first fact is x to the power of 1 is equal to x. And that's true for all x. And I'll say all x in real numbers. So any real number x, this equation is true. X to the power of 1 is equal to x. It's even true for 0. 0 to the power of 1 is equal to 0. And 0 is always the number that you should be checking in these cases, right? We've seen a lot of sort of funny business when it comes to 0. So yeah, in this case, even 0 to the power of 1 is equal to 0. But 5 to the power of 1 is equal to 5. 19 to the power of 1 is also equal to 19, etc. Here's a much more, or a much less obvious fact. X to the power of 0 is equal to 1. And this is for all real numbers x with x not equal to 0 itself. So it works for every number except 0. So any number to the power of 0 is equal to 1 except for 0. So in other words, 0 to the power of 0 is it's not well defined. It is what we would call an indeterminate form. So effectively what that means is that it can be equal to some things in certain situations, but it can be equal to effectively any value that you want. So it depends on the context. So right out the gate, if you just look at 0 to the power of 0, then it doesn't make any sense. But in some situations, like when these are variables, like if you have like something like x to the power of y, and it's in some kind of context, sometimes 0 to the power of 0 can be equal to something. But that is a topic for calculus. That's one of the major topics in calculus, is how to look at 0 to the power of 0. So we're not going to look at 0 to the power of 0 today, but we will look at x to the power of 0 equaling to 1. So those are those are the facts that we need going forward. I'm gonna write out all of the rules that we're gonna use today. Okay, where are we? I'll just start a new page here. So these are the rules that we're going to be using today, and I think that these are rules that I'm fairly certain these are rules that you've seen before, based on some of the stuff that we've looked at already. So these are the exponent laws. Okay, so the exponent laws, there's quite a few of them, but yeah, we'll just go through them one by one. Okay, so the exponent laws are the following. You have, let's see here. Yeah, I just want to make sure I'm doing them in the right order. So we've got the product law, or I guess in this book they're calling the product rule. So let's call it the product rule. Okay, so the product rule is that for any two numbers, or I guess any numbers, let's just make some guidelines here. We're gonna have the base of the number be a and b, and the exponents are gonna be x and y. So a to the power of x times a to the power of y is equal to a to the power of x plus y. Okay. By the way, I'm just gonna do one more little piece of terminology here. Sorry, I'm kind of all over the place. I'm a little when you're running behind, you feel flustered for the rest of the day. I'm gonna be like this for the rest of the day. My brain is just not settled. So I want to show you just a few more terms. I'm gonna make these nice and big. So if we have a to the power of x, x we call the exponent. Okay, a we call the base. And the whole thing, like this whole entire thing, all together, is called a power. Okay, so the base is a, the exponent is x, and the whole thing all together, like considered as one thing, is a power. So a to the x is a power. Okay, in fact, we could call a to the x is a power of x. Okay, that's another way of saying it. So those are terms that I'm going to be using. Base refers to the number that we're multiplying repeatedly. Exponent is the number of times we're multiplying it by itself, and the power is the whole thing considered as a whole. Okay. Anyways, the product rule. So the two bases. If the two bases are the same. Then we add the exponent when we multiply them together. It does not work if the exponents are, if the bases are different. The bases do have to be the same. So I'll give you a quick example. So like 2 to the power of 3 times 2 to the power of 5 is equal to 2 to the power of 8. Okay, which is, what is that? I think it's 64. No, it's not. It is 256. Yeah. Okay. Okay, so that's the product rule. The next one is the quotient rule. Very similar. Not quotient. Quotient rule. So the quotient rule is the following. The quotient rule is where you are dividing two different powers with the same base. So that happens when you have a to the power of x divided by a to the power of y, in which case you subtract. So a to the power of x minus y. While I'm writing these, if you wouldn't mind just writing in the chat, just confirming that you have seen these before, because I'm fairly certain you have seen these before. But if you haven't, I'll spend a little more time with them. So just let me know in the chat if these are looking familiar. I'm not asking if you're like an expert. Like I'm not gonna get you to answer a bunch of questions on the spot. But if you could just let me know if you have seen these before, it'll help me out. Okay. So an example of the quotient rule is if I had like 12 to the power of 4 over 12 to the power of 3, that would be equal to 12 to the power of, well, 4 minus 3 is 1. And 12 to the 1 is actually just equal to 12. So there you go. So the nice thing about the quotient rule is, can you imagine having to calculate? Yeah, you did do these. Okay, that's what I thought. So can you imagine having to calculate 12 to the power of 4? Like 12 times 12 is already 144. So 12 to the 4 is 144 times 144. It's a big number. And then dividing that by 12 to the 3, right? So the quotient rule can really just make things easy for us. Like we don't have to actually deal with those exponents. Okay, that's the quotient rule. The next one is the power rule. The power rule. Okay. So the power rule is where you have a power of a power. So that would look like if I have a to the power of x all to the power of y, that's equal to a to the power of x times y. So in this case, you multiply the exponents. So for example, 3 to the power of 7 to the power of 5 is equal to 3 to the power of 35. That's a big number, by the way. 3 to the power of 35. That's a bigger number than I can count to. Yeah. So something to keep in mind is that exponents grow very quickly. So the bigger our exponent is, like when we have a really big exponent, that makes the number extremely big, like really, really, really big. So like that's probably like the number of pieces of sand on planet Earth. That would be, I mean, that's my rough estimation. I have no idea how many pieces of sand there are, but I imagine there's many. And 3 to the power of 35 is a very big number. So like it's astronomically large. So yeah. Okay, I guess we could figure out how many digits is in that number. I think that if you punch it into a calculator, it'll tell you how many digits it'll be. So let's see. My guess is the calculator is going to give me a error. 3 to the power of 35. Yeah, it's 16 digits long. That's, yeah, so it's 5 times 10 to the power of 16. So just as a kind of like neat piece of trivia, so this is approximately equal to 5 times 10 to the power of 16. So 10 to the power of 16, right, that's 16 digits. So that's a big number. Okay, so we did the quotient rule, we did the power rule. Okay, product to a power. So I like to call this one the distributive property. For exponents. Okay, so this is the distributive property for exponents. So the idea here is that exponents distribute over multiplication. Okay, exponents distribute over multiplication. So if I have something like 2x in brackets and I take that to the 4th power, well, this exponent is going to be distributed throughout the multiplication. Keep in mind, exponents do not distribute over addition, right? If you have a sum inside of these, well, we've seen what happens when you have a sum taken to a power, right? We've looked at situations like that, and you don't just copy the exponent down. This only works for multiplication. So I'm going to make a quick note of that in a second, but this would be 2 to the power of 4 times x to the power of 4, which happens to be equal to 16 times x to the 4. Okay, so I'm just going to make a quick note here. So note, exponents distribute over multiplication. They do not distribute over addition. So, for example, the same example here, except with addition instead of multiplication. So if it was 2 plus x to the power of 4, that is not equal to 2 to the 4 plus x to the 4. These are not equal. And we've seen many situations. Oh, awesome. I love this question. I've been wondering why x to the power of 0 doesn't equal 0. Well, we can do that. I will show you in just a second. Okay, so we've got a couple more rules to go over, and then I will show you why x to the power of 0 is equal to 1. That's a fantastic question. It's a really, really important question. Okay, raising a fraction to a power. Okay, so fractions. Oh, I had it in green before. Okay, let me change that to green. 1 second. Okay, fractions to a power. Okay, so if we want to take a fraction to a power, this is what it's going to look like. So if I have, let's say, a over b, and let's say we want to take it to the 7th power. I don't know. Well, that will be a to the power of 7 over b to the power of 7. Oh, actually, this is supposed to be the general case, so this should be in x, right? So this works for all numbers. So, of course, the only time it doesn't work is if b is equal to 0. So I'll just make a quick note that b cannot be equal to 0 here because it's in the denominator. Right? We always have to be careful of those things, right? Okay, so for example, e.g., let me center that properly. e.g., let's say we wanted to do 2/3 taken, and let's square it. That would be 2 squared over, no, let's cube it. Let's cube it to make it a little more interesting. 2 cubed over 3 cubed, which of course is equal to 8 over 27. Okay, so that one's not too bad. And negative exponents is next. Negative exponents. Okay, so that's when the exponent is negative. Doesn't really matter what the base is, as long as the base is non-zero, and we'll see why in a second. So if I have a to the power of negative x, that's equal to 1 over a to the x, and in this case we have to make sure that a is non-zero. It does not work when a is 0, because then we would be dividing by 0. I should also point out that it works in the reverse order. I should also say that we have, if 1 over a, I'll use a different letter just to make sure that you know that this is a different situation. So 1 over b to the negative x, or let's do b to the negative y, just to make sure that we're not, this has nothing to do with the first situation. This is equal to b to the power of y. Okay, so you can kind of go back and forth. So you can change where an expression is in the numerator or the denominator by taking it to a negative exponent. So that's really handy. So for example, 2 to the negative 3, that's equal to 1 over 2 to the 3, or 1 over 27. Okay, so that one's not too bad. Yeah, I think, oh yeah, and then there's one more situation too, which is really similar to the negative exponents one. I'll just continue on. Actually, you know what? I'll just keep it within the negative exponents. So another situation is if we were to have a to the power, or a over b to the power of negative x. This is equal to, well, what happens is we would have b over a to the power of x, which we would know to be, oh, you can't see that, which we know is b to the x over a to the x. Okay, so this one's slightly, maybe a little more complicated than the others, but the idea is that what a negative exponent does is it reverses the numerator and the denominator. It's saying instead of multiplying many times repeatedly, we are going to divide many times repeatedly. So that's what the negative exponents do. Now I'm going to leave this last one for just a minute from now. I want to take a moment just to address this question that came up in the chat. It's a really good question. So we're just going to pause with our rules, because the next rule is kind of a big one, and I want us to spend a lot of time on it and to focus on it. I don't want to have to go back. So let's address this question. So question, why is a to the power of 0 equal to 1 and not 0? So why is it equal to 1, not 0? Everyone tends to think that it should be equal to 0. And that would be true if exponents were multiplication, right? A times 0 is 0. But a to the power of 0 is, yeah, it's not 0. It's not 0. It is definitely 1. And I'll prove it. I'll prove it. Okay, so take any non-zero number. Take any non-zero number a. Okay, So that's our number a. That's our variable. So this can be any number except 0. Because 0 to the power of 0 is not equal to 1. It can be equal to anything. I already talked about that. So take any non-zero number a. Okay. And let's do okay, so what we'll do is we'll notice that a over a, well, what's that equal to? Well, it's equal to 1, right? Anything divided by itself is equal to 1. Well, a to the a, well, let's just change this a second. Well, a, I know that a is equal to a to the power of 1, right? And so is this one. This is also a to the power of 1. So this is a to the power of 1 over a to the power of 1. Well, if we use the quotient rule, so I'll say using the quotient rule, I'm going to write the QR, the quotient rule, because I don't have room. We know that this on the left, let me change the colors so you can kind of see where I'm going with this. So I'll change the color to, how about purple? Oh, color, purple. There we go. And then I'll use purple over here. There we go. Okay, so using the quotient rule, if I have two powers divided by each other and they share the same base, what I do is I subtract the exponents, right? I've got a to the power of 1 minus 1. That's equal to 0. Okay, that looks good, right? Because a to the 1 over a to the 1 is equal to a to the 1 minus 1. And you can probably see where this is going now. A to the 1 minus 1 is 0, a to the 0. So a to the 0. Oh, this is supposed to be equal to 1. I don't know where that 0 came from. I told you I've got a scatterbrain today. I didn't do anything on this side of the equation. This side of the equation is completely the same. I haven't changed anything on this side of the equation. So all of this is equal to 1. No idea where that 0 came from. But yeah, a to the power of 1 minus 1 is equal to a to the power of 0. And this whole thing is equal to 1. Okay? So hopefully that answers your question. That's why. Sort of a more intuitive way of doing this, like if you're not satisfied with this, by the way, when we finish mathematical proofs, what we like to do is follow it by a square. So that proof is over, and Goose is coming to say hi. Say hi, Goosey. Hi, sweetie pie. Yeah, okay. So, okay, now, okay, bye, Goosey. Where was I? If you want a more intuitive understanding of this, what I think of this is, like, you can think of a to the 0 as a blank slate. Okay, it's empty. It's like it's waiting for more exponents. Okay, a to the power of 1 is, what you do is you would multiply a to the power of 0 by a, right? Because it's repeated multiplication, right? So if a to the power of 0 was equal to 0 and we multiplied it by a, then we would always just be staying at 0, right? So so a to the power of 0 is kind of like your empty exponent. And since exponents are repeated multiplication, the sort of the unit of multiplication is 1, right? It's not 0. Right, so it's kind of like the empty slate for multiplication. So we have to be able to multiply it by something, and if we multiply it by 0, then it's always going to stay at 0, right? Okay, so so hopefully that answered your question. Let's talk about this next step, fractional exponents. Okay. And let me know in the chat if you've seen fractional exponents before. That part I'm not sure if it's review for you or not. But we'll talk about fractional exponents. So fractional exponents. Okay. Okay. So I guess we'll just write it as a rule. I think that's probably the best way to do it. I'll write it in two ways. So a to the power of 1 over n is equal to the nth root of a. And here, I think it goes without saying, n is non-zero. So you cannot have the 0th root of a number, and that's because you can't have a denominator of 0 in your fraction, right? You can never divide by 0, even if it's in your fraction. It never works to divide by 0. Similarly, we have something very similar to this. If I have a to the power of m over n, that is equal to, well, it's equal to a couple things. It's equal to the nth root of a to the m, and I'll close this little square root like that so you know where the square root is ending. But it's also equal to the nth root of a all to the power of m. That whole thing. So these two things are all equal. Okay, so we did a little bit of it. Okay, at the end of the semester. Okay, cool. So we'll continue on with it now. Okay, so let's do a few examples. Okay, we'll do a few examples. Okay, let's just do something simple. So x to the power of 1/2, that is equal to, well, the square root of x. And we don't usually write that 2 there. We usually ignore that 2 when we talk about square roots. So we don't, oops, not 2x. So we don't actually have to write that 2, okay? So let's try a couple more. Let's do the 4th root of 2. Let's do the 4th root of 2. Well, we could write that as 2 to the power of 1/4. Okay, that's not too bad. Let's say let's do I'm just trying to find a good example. Let's do 8 to the power of 4/3. Okay, let's do 8 to the power of 4/3. So this is equal to, so the 3rd root of 8, all taken to the 4th power. That's cool. And look at that, we can simplify this. So the 3rd root of 8 is 2. So this is equal to 2 to the 4, which is equal to 16. So 8 to the 4/3, who'd have known? That's equal to 16. Isn't that funny? Okay, now this is where things get interesting, okay? So this is where we'll actually do maybe a little more like problem solving. So I'm going to give you this question here. We are kind of running out of time, but I might go a few minutes over because I showed up late. Let's see here. Okay, so I'm going to get you to do this one. I'm going to give you 1 minute to do it. I want you to try your best. So I want you to simplify 4 to the power of 3/2. Okay, I'm going to give you 1 minute to do it. There we go. And go. Okay, Let's have a look at this one. Give me just one sec here. Yeah, okay. So what we're going to do is we're going to write this in the following way. So this is going to be the square root of 4 to the power of 3. And, well, the square root of 4 is equal to 2. That's 2/3, which is equal to 8. Simple as that, yeah. Okay, it looks like a lot of you guys got that too, which is awesome. Okay, how about this one? Okay, we're just gonna go through these ones in the book here. I like these ones here. So this is the 5th root of 32 to the power of 4. Okay, give you another minute to do that one. Okay, goes. Okay, let's try this one out. Looks like a few people got this one. Okay, so yeah, one way to do this is to, yeah, absolutely to write this as a fractional exponent. So to do 4/5. But the thing about that is, you could rewrite this as 2 to the power of 5 to the power of 4/5, right? Because that's what 32 is. And, well, these 5s would cancel. So this is actually just going to be 2 to the power of 4/5 times 5, which is 2 to the power of 4, which is 16. Yeah. Okay, we'll do a couple more. I think that these are really good questions. 16 to the power of negative 3/4. Okay, so another minute to do that one. Let's see how we do. Okay, let's see where this one takes us. Okay, well, let's get rid of that negative. So this is going to be 1 over 16 to the 3/4. Okay, and that's going to be equal to 1 over, what would that be? The 4th root of 16 all to the 3rd power, which is, okay, hi Goose. 1 over, well, the 4th root of 16 is 2. So we got 2/3, so this is equal to 1/8. Okay. So, oh, it looks like a lot of you guys got that same answer. That's awesome. Good job, good job. Okay, we've got 2 more questions that I want to do. So let's keep up this pace. So I've got the 3rd root Okay, Goose is trying to play with my pencil now. I've got the third root of 4 over the fourth root. Okay, Goose, you're very cute, but we don't need that right now. Fourth root of 2. Okay? Tricky one. This one might take more like 2 minutes, but I'll still give you 1 minute. See how far you get. This one's tricky, but you can do it. Okay, that's enough. Okay, so we're gonna what we're gonna do is we're gonna write each of these as a fraction. Okay, so we'll use some fractional exponents. So this one over here, this is 4 to the power of a third. Okay, Goose. Oh my gosh. Okay, 4 to the power of a third over 2 to the power of a quarter. Okay, so that looks all right. And let me write that fraction nicely. 1/4. Okay, now I'm going to write this 4 as a power of 2, right? Because I think if I do that, then I would be able to share the same base. So this is actually 2 squared to the power of a third, all over 2 to the power of a quarter. And this gives me, well, using the product law, or sorry, the power law, I'm going to multiply those exponents. So this is equal to 2 to the power of 2/3 over 2 to the power of a quarter. Okay, and this is equal. So now I've got the same base, right? I've got the same base. So it's 2 to the power of 2/3 minus 1/4. Now on the side here, I'm going to just quickly do what 2/3 minus 1/4 is. So I have to find a common denominator, which is 12. So I multiply this one by 4, this one by 3. So I've got 8 minus 3 over 12, which is equal to 5 over 12. So this is equal to 2 to the power of 5 over 12. Or if you really want, you could do the 12th root of 32. That would work fine as well. Awesome. Looks like some people got it. Like I said, this one should have probably taken at least 2 minutes. This is kind of a more challenging one. Okay, this one I'm going to leave for your exit slip. It's certainly the most challenging one. If you can't do it, that's fine. I still want you to fill out the exit slip. But yeah, so here it is. So we've got the third root of 9 times the fourth root of 27. Okay, so that's your exit slip for today. Exit slip. Okay, so there's your exit slip for the day. If you need a little bit of help formatting it, you could always use Desmos. Remember, you can use Desmos to write sort of complicated math expressions and then copy and paste the plain text into the Google form. So whatever you like, or you can just use like this. You know, you could write the square root of maybe it's the square root of 7 or something. I don't know. So yeah, there's your exit slip. And if you're really struggling and if you can't solve this one, just let me know, because this is intended to be a very challenging question. But yeah, so there's your exit slip. And I should talk a little bit about the final exam. I looked at your what's the word I'm looking for? Responses. I looked at your responses, and it looks like a lot of you actually want to do a final exam. So like a traditional final exam. So we are going to do a final exam. However, if you would like to do a project in lieu of a final exam, I will allow that. So I'm going to give you an option, but it seems as though the majority of people want to do a traditional final exam, so we will go ahead with that. And I'll give you more details about the final exam over the coming weeks. And yeah, so that's where we're at. So yeah, if you want to do a final project instead of a final exam, I'll tell you what some of the expectations are and what I'm looking for and what the scope is going to be and all of that. But it seems like most of you want to do just a traditional exam anyways, so we'll just stick with that. So I'm gonna sign out, and I'll talk to you guys on on Tuesday. So am I gonna send you an answer key? Yes, I will. Okay, all right, take care guys. Bye bye.